Hey everyone. So this is on. Stop streaming, auto stop. Okay. Sorry. I'm not used to this new setup. Yeah, so this is calc mode, right? Let's see. Right here, what I'm showing on the screen right now is a calculational proof, calc mode proof, right? Where we're doing some calculations and basically using algebra to show something. So let me see if I can make it just a little bigger. And what I've got here is I've got some, proof about this prime sieve I'm working on. And basically, I've got a operation. So R is this thing called a rake, which is just a data structure that has a bunch of arithmetic sequences in it. And we've got two numbers, J and M. Actually, this is redundant. So we have J and M, and we're going to say that we're going to partition these sequences on the letter J, on some number J. And I'll show you what this means. All right, so right here, we've got this rake. It has two numbers in it, 5 and 7. So these are the so D is 6. What this is, these are two sequences that are the numbers 5 plus 6 times n and 7 plus 6 times n. Okay. And then I'm going to take this sequence right here. So this is R, and I'm going to partition it on the number 5. The idea is that we're in a prime sieve, right? We've got two sequences in here, and they contain all the prime numbers, and in fact every number, right? That is not a multiple of 2 or 3, or it's not 0, it's not 1, it's not a multiple of 2, and it's not a multiple of 3. So that gives us these two lines, and they contain all those prime numbers. This is basically the root of the twin prime conjecture, right? So we've got these two sequences that are, two items apart, and then for the foreseeable future, it could be possible for any two of those to have a prime number for the same n. So at 0, of course, they're 5 and 7, and at 1, they would be 6 plus 5 is 11, and 7 plus 6 is 13, so 11 and 13, and then 17, 19. So you got twin primes, right? And they peter out after a little bit, but there's a bunch of them. Of course, right here, 23 and 25 is not prime because it's a multiple of 5. And so what I do in the sieve is we say, well, okay, so we've identified 5 as the next prime. We got to this point, and then we see that the first number here, in our system, right? We're basically enumerating all the numbers that are, we're going to take one from this one, one from this one, one from this one, one from this one, and those are going to give us all the numbers. So if we say eval r terms 10, so you can see that it's these numbers, right? Which is the same as what we're getting down here before. And so what I wanted to do was partition this, right? So meaning that instead of having just these two lines, I want to apply apply this so that partition is taking this and turning it. Oops. Wow, what am I doing? My finger's on the wrong key. That's what. I keep hitting. Yeah, I keep hitting left when I mean to say R. Sorry. So I want to put in 5 times 6 5 times 6, or sorry, 5 plus 6 times, and then for n, I'm going to plug in 0 plus 1n, right? And then I'm going to plug in 0 plus 2n. And I'm going to plug in 0 plus 3n. Oh, sorry, no, I'm going to plug in, wow, that's not right. I'm partitioning on the number 5, so I'm putting in the number 5. I'm putting 0 plus 5n, 1 plus 5n, 2 plus 5n, and 3 plus 5n, and 4 plus 5n. Right? And then these work out. These work out to this is not calc mode, but this is similar to calc mode. This is kind of like what calc mode feels like. But we say 6 times 0 plus 5n, so we get 5 plus 30n. Sorry, 5 plus 5n, because the 0 cancels. Oh yeah, 5 plus 30n, yeah. That's right. They're all going to be 30n. And then this is going to be 5 plus 6 times 1 is 7, right? So 6 times 1 is 6. 5 plus that is 11. 11 plus 30n. Right? 6 times 2 is 12. 5 plus that is 17 plus 30n. And so on, right? Okay. And so that's where these numbers come from. So we have 5, 11, 17, and then the next one is 23, and then 29. And then the other numbers are coming from the 7 times 6n, right? So we're plugging these in, and also these same 5 sequences in there. And then in each case, one of these will produce nothing but multiples of 5. So 25 here, this this one 5. In this case, it's 0. So 5 plus 30n, well, that is 5 times 1 plus 6n, right? Yeah, right. And so you're always going to produce a multiple of 5, no matter what number you plug in. So you're multiplying this arithmetic sequence by 5. And likewise, so whichever one produces this one, which I guess probably would be this right here for, so it would be 7. So switch over to 7 plus 6 times, yeah, same thing. So we're going to 6 times 3 is 18 plus 7 would be 25, right? 25 plus 5n, which is right. And then, so same thing over here. This is 5 times 5 plus n, right? So which term it is? So here's the 0th term, and here it's the third term. But one of the things that we produce is going to be always just multiples of 5. That's the purpose of this step, right? Is to partition these sequences into a bunch more sequences, but where some of them are purely multiples of the prime number that we want to eliminate. And then we're going to cross this number out. So we're going to remove this, and we're going to remove this, and that's the next step. And now we've produced a new set of sequences that no longer contain any multiples of 5. And now we say 7 is the new prime, the new next prime, and then and then that's how a prime sieve works. You find the next prime, which is the lowest number that you haven't crossed out, and then you cross out all the multiples of that. And as a little, as a bonus, you can start with 7 squared or whatever. So anything that's in our sequence after this that is less than 49 is going to be prime, right? So that's the idea. of what I'm working on, right? And to do that step, what I'd previously done is I had this implementation that that's now called partition 0. So it takes the rake, which is this data structure, and partitions it on some number n, and it does all this stuff. And it does it by basically mapping, by generating, so the rake contains the d, the delta, the slope of the lines, and it contains the, that's the number you multiply by n, not this n. That's why I changed the name to I over here. So maybe change this here as well. Call this I. And probably this should be called I as well. Okay. Okay, so it contains the d term, and it contains a bunch of constants, and they all have the same d, and then they have they'll all have the same delta, so the same slope. Hence the name rake, right? It's like your bunch of parallel lines. And then we will do this partitioning step, and it takes the constant. So our sequences takes the constant terms and generates the arithmetic sequences. So inside this little sequences section, you can see that in order to get a sequence, we are mapping each k in the list of constants through this async function, which is in another file, and it just generates another data structure that is the arithmetic sequence that takes those two numbers. And so I thought that was complicated, and whenever you deal with two, like every data structure you want to deal with, you have to unwrap it. And so I found that I wanted to just inline everything and make it simpler. And so I wrote a new definition of partition here that just ignores all these arithmetic sequences. It doesn't go through that step, and it just directly does one mapping, right? So we take the range of numbers. We know that we're multiplying by, here I called it j. I should have called it j up here then. Sorry, I went through several variations of this number, of this naming of this thing, because I kept running out of names, and like some other name was a better name at each step, like I for index and whatnot. Okay, so j is the number that we partition on. So we multiply the number of arithmetic sequences by j at each step. and so these two things do the same, right? So these two implementations do the same thing, right? So this is obviously much cleaner because it doesn't go through this secondary data structure, and because it doesn't go through this data structure, I don't have to jump through hoops to figure out what the size of it is, right? Because here I was doing a mapping, and the individual arithmetic sequences created their own partition. So for each arithmetic sequence, I got a bunch of arithmetic sequences, and then I had to stick them all together with this join operation. And so then to calculate the size, I have to prove that the one of the features of the rake is that it's not empty, right? So if you don't have any constants in it, how do you can't get a term out of it? And so I have to have a term inside the rake. I have to have a sequence inside the rake. I have to have a constant term inside the rake. I have to have a constant, at least one constant inside the rake in order for it to generate terms. And so that's a property that has to be adhered to. And that means that list cannot be empty. Well, the proof is that this, you have to do this proof. You have to figure out, you have to show that it's not 0. And so I had to do all this work to show that it's not 0. And it's not code. It has nothing to do with the implementation, right? The implementation is really just this line right here. Just partition each sequence, join them together, and then take out the constant. So these two lines right here. But then I have to prove, or at the time I had to prove that the length was such and such, and for a while I had to prove it was sorted. This is actually shorter than it used to be. So now I just say that it's not sorted, and don't worry about it. And then I don't have to. That wiped out two other proofs, or at least one other proof, and then now it would be two other proofs. So that wiped out a bunch of work. But even so, it's a mess. Like this is all junk. these two lines are the ones I want, and then at the end we just say, okay, I'm returning a new rake that has this delta term and then these constants, right? That's it. But I need all this work to prove the size because I'm doing this junk. And it, I've actually learned some stuff since then, and it's possible that this might, it's possible that I could have just written this. KS. I don't know if this will work or not. If this works, I'll be. No, okay, so yeah, that sometimes when you're dealing with array operations, you can get it that simple, and I didn't realize it was that simple, but it's not in this case. So whatever. Right, so that proof is there, and I'm leaving this intact, other than changing the variable names, because there's a chance that what I'm working on now is just not going to work out. Anyway, I rewrote it like this, and you can see that. Not only is it much simpler, but I just, there's no join operation. What I did is I just created a new. I know what I decide up front that I know that the length of this thing is going to be, this product. It's the j times the length of the old list. And then I'm just going to create new constants using math, right? And this math was not obvious to me, but the intuition. So this is J, another programming language I used. And so what's happening here? You don't need to read this. Just ignore all this. The picture is the output, right? So I have the inputs 5 and 7, and I have the number 3 is the number I want to multiply by. So maybe I should make it 5 over here, right? And what I want to do is I want to have this pattern. I want to have 5 7 5 7 5 7 5 7, and I want to have 0 0 1 1 2 2 3 3, and then those are the two patterns of numbers that I want to generate. And so what this says in J is this says take the floor. So first of all, I is just counting up to that sum 5 times 2, so 10. It's counting up to 10. It says this is X, this is Y. And it says, so I is two numbers, and says I is the integers from 0 up to, basically range here. I dot is range. And it's 5 times the length of this list. So I dot 10, so I equals I dot 10. I is just a variable, which is, I is those numbers. So I'm taking those numbers, and then this says, okay, now ignore all that, and give me y, which is these two numbers. So I'm saying 5 and 7, yeah, that's y. And then from 5 and 7, I want to extract these two things. So over here, so I got to call this y. Y is that, and then we say y that, and we get that sequence, right? And then if we put in this one, we'd get the other sequence. And then the semicolon puts them in boxes and separates the two lists. But you have to put it in parens here. What? Oh, right. No, sorry. Never mind. Forget I said the paren thing. So there you go. Those are the two things I'm doing. And then the idea now is that I take these numbers are the these are the numbers that I want to add here. So these are the 0 and the 1 and the 2 and the 3 and the numbers up to 5, right? 0 1 2 3 4. But I want to kind of alternate between the two sequences, right? So I want to pull one from, that, because that's what term does. I want to pull one from the first sequence, one from the second sequence, one, and so on. And so that's how this is all calculated. So I want to pull the 5 and then add 0. I want to pull but not just that. I want to pull. Okay, so I want to say for each one of these, I want to say 6 times the left thing plus the right thing for each but actually it's each pair, right? So I would say boom, and maybe transpose it. Yes. Right, and I'll put that in, and then, oh, wrong way. I want to do that for each line. Nope. I want to play 6 times the right thing. Oh, what? Right. Sorry, that's not how J works. J. Okay, that's a little closer. Wow. Okay. I want 6 times this plus this. Is that not what I wanted? 5 plus 6 times that plus, yeah. No. There we go. That's not right either. Well, it doesn't matter. I'm just looking like an idiot and I'm off topic. It's 5 plus 6 times this. We want to multiply 5, which is the right-hand side, plus 6 times the left-hand side. That's this. Oh. No. What have I done wrong? 0 and 5. Let me just... Oh, I put 6 and. No one. I just put 6 on all of them. Oh, wait. Wow, I did not think that Jay would do things like that. Why is it giving me? I'm not clear why I get 5 7. Like, why am I getting these 6s? And they're coming from here, but why isn't? Sorry, this has nothing to do with anything I'm talking about. I just learned something about Jay. I do not understand. Clearly, I think the rank of this is slightly different. Yeah, this is something I've never experienced this. I don't know what this is. All right, sorry. I went to say 6 and times at this. That's looking a little more promising. And then when we add them together, we should get the prime numbers. Yeah, okay. There we go. Sorry. All right, so 0 plus 5, 0 plus 7, 6 plus 5, 6 plus 7, so on. You have to multiply in the 6 by that constant term. That's what I was getting at. Anyway, all right, so yeah, like, it was confusing, and that's why it was confusing just to figure out what little algorithm to use to do this. I don't know if you can see this or not, but it took me a bunch of tries just fiddling around with different expressions. That's why I was using J as a calculator to figure out the right way to say that, the right way to say this. And then once I got it, I put it into Lean, and it worked. And then I spent a long. In fact, I wrote a whole. Let's see if I find my my thread on the Zulip channel. Zulip. I posted something today. And I was like, okay, I've got. First of all, I asked, how do I even do this? This was after I, simplified it down to just, I took out the rake thing just so I could share it and ask the question, because I couldn't figure out how to prove this. That you do the partition step, and here I just turned it into a list and I just stuck a D and a J in there, and I couldn't do it at all. Later, I came back and I figured out that I could do it by, the problem is this, right? Yeah, you have to, this little exclamation point says you have to, basically you're proving that that this expression is in bounds. This doesn't really matter. But anyway, we got it down to a couple lines. So I asked for help after I proved it. I asked, okay, well, I don't like it because it's like I've got, here I've got a proof inside of my type, right? Like this is the type of the thing I want to show, that this is a theorem and it has a proof inside the theorem, right? Which is weird. And I was like, is that really necessary? And the answer is yes, it is necessary, but but you don't have to make it explicit or whatever. Anyway, this doesn't matter. So I got it down to this, and I was like, okay, cool. So now I have a proof of the fact that so here's the definition with just taken outside the rake, and then here's the proof that it's this long is just simp partition, which was new to me, and this is the theorem that basically the indices, basically that there's a mapping. What I wanted to do is I wanted to take this formula that I came up with, right? So I did list range of these numbers. So just these are the counting numbers again. This is I dot in Lean, and then we're going to map it with through some function that takes one of those numbers and does this, right? And it pulls the old thing out, does the modulo, and then it does the division and multiply by d. Okay, so it's basically, this is making this pattern right here. Okay, and then I wanted to extract this function so that I could use it in a proof. And that was the intent. So this took me like a good chunk of the day, and then I went to write the proof. I shouldn't have done that. I need to close that. I would lose that window. Okay, Control Shift T. There we go. All right, put it back on. And then well, then I went to write this proof, right? So I've got partition now. I've got the length of the partition. This is how it looks like once it's inside the rake, right? It's a little bit, it's still that same line basically. Just now, instead of just the list, I've got the r.k, r that for the rake and the constants inside the rake, and then I've got the little proof that the index I'm using is valid, and so on. And basically, this is that line of J translated into Lean and stuck inside my actual data structure. I still have to prove that the length is right, but now it's just 2 lines because I have this little thing, and then I build the new rake structure, and it's easy. And then I need to basically duplicate this line so that I can use it in a proof later. So that's this. ks prime length is equal to whatever. So this is the r partition whatever dot ks dot length. After the partition, the length of the constants is this j times rs, the original length. And here is the same thing. So I need to extract this. And again, simp came to the rescue. This is my example code. Here's why I'm doing it. There we go. And then here's the theorem that I wanted to prove, that there is this relationship between the constants of the previous one and the constants of the next one. So every constant exists. Right. So my thought was at the time, and this still seems like a reasonable way to do this, is that I was going to take this fact that I had this formula that related all of the constants of the old one to the constants of the new one, and I have the new delta, which is just I might need a theorem for this, but it's just r times d times, or, it's the old delta times j, right? So the slope I just multiplied by j, and the list length I multiplied by j, and that's it, right? And so it just scaled it up basically. And I have previously made, I don't know if I've talked about this on camera. This might have been since my last session, but I have a theorem called term if, which you can see in that pop-up there. So it says that if there is if there is an n that you can plug in to get the letter, the number m out, that is the same, that is equivalent to, or that is true if and only if there is some constant in the list of constants and some x that you can plug in, so that the constant plus x times the delta is equal to m, right? So this is basically a formula that says what it means to have a term. And I was able to use that to prove that the sorting operation, like so the sorting, this theorem right here is actually about sorting, and it's saying that it's a proof of this theorem, right? Well, okay, it's taking that same idea, but now it's saying on the left hand side, if there's a term that you plug in and you get n, then after you sort it, after you call r.sort, and that makes a little wrapper thing, and if it has a new rake and a proof about that rake. If you take the rake out of that thing, that's the dot val, and you ask for a term of m out of that, it's some new m prime, right? But basically, if you could get a number, if you could get n out before, you can still get n out now. And if you can get n out now, you could have gotten it before. So I didn't add anything, I didn't remove anything. They're exactly the same. The m is different because I sorted it. I rearranged the sequence, but the numbers in the sequences are the same, right? So the set is the same, right? Where basically the rake is modeling a set of numbers, and only sometimes are they in order. Only when you have this sort flag set. And you set the sort flag by calling sort, or sorted flag by calling sort. So if R is sorted, then it's trivial because you just call unfold sort. I bet this could. I wonder if this could be D. Then simp sort. Nope. Wow, that's interesting. I'm starting to expect. I don't know. I'm starting to expect simp to work, and it's not working in as many places as I was enlightened to believe it. Anyway, whatever. All right, so now, sort returns, it returns a new rake, so it returns, you give it an R and gives you an R prime, which is another rake, and it has all these properties. So it's the old delta and the new delta, or the new delta and the old delta are the same. So the D has not changed. The new one is sorted, and the new one, the constants are a permutation of the old constants that have now been deduplicated, right? So it's a permutation of the unique constant. So it is possible that you could have like the number 5 in there as many times as you wanted it. sorting gets rid of that because you're sorting by a strictly less than. And so in order for each consecutive pair to be strictly less than, you have to have it no duplicates. You can't have less than or equal to. All right. So anyway, I was expecting this proof to be horrendous, but because I had done the work of term if, that proof now it all went very smoothly. And term if, I don't think I actually showed it. It was fairly complicated. It was a lot of work to do, and yeah, but it came out kind of nice. So it's short, but it took me a long time to make this happen. I think this was my last video, right? Yeah, this is the content of my last video. It took 5 hours to make this happen, and this was what I arrived at the end of the video. So that's where I wound up, and then after I did that, I did a bunch of refactoring and cleaning up, and so now we've got I moved a bunch of stuff out. All the stuff about rake map, which is where we actually associate with a set, that's just moved to a separate file called rake map. And here I've added a bunch of sections, so now you can see these little sections up here. You can go to terms, and there's some structure to the file, so you can find things about it. Okay, and I guess these are the ones I need to work on. They have issues. Okay, so then, right, so in order to remove multiples of a thing, I have to call partition first, and so I'm working on a proof of partition. And I was working on this. I really like that navigation now. I didn't know this. I never saw it turn colors like that. Very handy. And so here's where I'm at. So now we're talking about calculational proofs. All right. So I went to write this thing, thinking I was going to use this function that I spent all day on, and I still think it might be useful to do that. But I had to write this thing. I want to write that. Well, what I was going to write was something very similar to sort, right? Let me bring that back up, right? Not this one, right? I was going to write something very similar to this proof that, if something, if the term exists, then after we sort it, I'm sorry, so right, so this would be, I just wanted to replace that with partition, right? But then it occurred to me that, well, actually, when you do the partition, the sorry, I'm not frozen up. I just had a thought in the middle of what I was saying. That what I was going to say is that if I have a term, then afterwards I will also have it. I will also have, after I do the partition step, I will also have that term, and they will all be in the same order. So the thought was that m and m prime are the same. And now I'm wondering if that's true. Maybe the reason, part of the reason I'm struggling here is because it's not true. I mean, right? So if I say eval r dot partition 5, right? So that's the same thing. Dot terms 10, right? And we should see. Why is this mad? Partition 5 has type. Oh, I have to prove that. No, by simp. I need this by simp thing. I need a proof that 5 is greater than 0. Which you would think ought to be. I wonder if I could just pull that in. Give me a second here. By simp. Oh, but not here. If I lose this, what does it work? Yeah. Okay, so now it works. I don't even need to put this in, unless it's not obvious, right? So this is guard is an assertion, right? So that's saying this is absolutely true. But the guard would be. We could also say this guard that whatever these are. So these are right, this thing, but these are these numbers right here, and we would say these are equal to each other, and the guard passes. Right. So that's the assertion I'm making, and then we can see what they are here, which is these same numbers. Right, because there's now 10 of them, and so the first 10 terms are just these numbers. That's how it works. But I think it's possible that this is not true. Oh, okay, right. So I did have this issue, right? So without this, then I think everything I've done so far will break. So this is the condition I was thinking about that gave me pause, right? So without that, and you have to write it like this. Do I break something? Nothing breaks, and so that might be part of the problem. The fact that I haven't used this fact might be like the step I need. It might be something I need. All right, so let's talk about calculational proofs, because I think I called this thing like I put on the title card something about the horrors of what I call it of leaning forward calc mode and the horrors of natural number division. So calc mode is awesome, but natural number division is terrible, and we'll see why in just a minute. So I'm going to put that up there. Okay, so yeah, I'm supposed to center me. It's not working. Okay, so right. So I realized that m and m prime are the same. So I just have this. So rather than having that some m exists, the m is now outside of here. So rather than exists m implies exists some m prime, I just have for all m, right? So when it's out over here, it's like a for all. So we can in fact, I think I did this. I had it written this way earlier. So for all m, this is true, and then you have to say intro m here. Either way works, but I also had m up here, so that was what was redundant. Either way works, but this is kind of the spirit of what I'm trying to say. For all, makes it's like I'm deriving a logical. Right, for all m, if there's a term m here, then you have it this way too. Right, it's the same before and after. And I guess I wrote it with this on the left, thinking it would be a simplification rule. And so So now I have to prove this. And so this, all the stuff I'm calculating down here is this. It's this statement. But what I do is I say we can watch it evolve over here, right? So the first thing we do is we have to make that statement. And so we have to prove this exact statement here. It did add an n for us. And then when I press down, it's going to show me what we need. So I introduce m, and m is going to show up here somewhere. So there we go. So m went away. From down here, I moved up here. Okay. And then I'm going to simplify this by, simplify it by expanding the definitions. So I'm going to see what the definition of partition, term, and we can see it step by step. So if I go to partition, that's after I apply both. I take this word. You got to click way over here. So this one expands to this, and we'll still see equals r term m at the end, right? So oh, interesting. I thought you could step through it. If you say unfold, you can step through it. I wonder if you get. If you say decent, you can step through it. Okay, well, whatever. I guess simp kind of works. Yeah, so that's whatever. I guess if I did this much, right, then I would say, I want to say simp. Then we would have some more of this to do. There we go. So after simplifying it this much, then we have this A sequence, and then if we simplify that, then we have to simplify the term from that other class, and we get this and this and this. This is all what term itself means, right? So the steps would be like simp term simp list get. And now you can walk up and down the list of. Oh, you can't do it here. What's wrong here? And so list get is not working when I don't have it. Whatever connected, doesn't matter. All right, let's just put all this stuff back. Point is that if you expand all these definitions, you wind up with something that's pretty complicated, and these are the getting something out of the list of constants, and it's really messy. But there's really two things you're getting out. You're getting m mod this m that the number you're feeding into the term function. So that's the parameter to term. That's mod the you're doing some modulo operation because again you're pulling one out of you're pulling from each sequence in turn, so you have to do the remainder operation, divide and take the remainder, figure out which sequence you're pulling out of, and then you also do something with again, brain. I just had an idea here. that could save me some time or whatever. We'll see. Because I made this definition up, so if it's hard for me to simplify, I could go change the definition. And we're about to see the pain that I've been hinting at, right? All right. Anyway, so but we have these two things that we have to get out, and then like actually, this is the only get operation is the original constant, right? So there's a bunch of rewrite rules or I guess the definition has happened, and so now what we should be seeing is that this on the left-hand side of the equal sign. Let's see if I can isolate. One of these things will give me the plus. Okay, so this sum right here in blue now is the left-hand side. All of this is this right here, and then everything on the other side of the equal sign, this equal sign down here. So this line is this sum. So these two sums are the same, or at least that's what I'm trying to prove, is that these two sums are the same. And so to do a calculational proof, first I'm going to give some names to these things. So first I'm going to take this this thing. So this is m mod the length of the list. So the remainder after dividing by the length of the list of constants, and then the little dots are a proof that it's a proof that the array, the list index is valid, right? So it's not out of bounds. So you never get an out of bounds error, right? But you have to provide this. All right. So when I say I is equal to this expression right here, this mod expression, that's I now. It's this number, and then K is going to be the entire thing, including the proof. So it's so that's what this. You see these little angle brackets? Well, they're So if I do this term right here, and then I move to the next line, like you see that went away, and then now this it doesn't actually render that way, but conceptually this has been replaced with I, right? You can see that I is now this, and so they're the same. And then if I go to the next line, then all of this will go away, and it'll just be called K. Right? And so K is here with the proof, and then now in here we just have the word K. And you can see it's a little hard to see, but that's in green now to show that's been added. Okay, and so then we have this big long thing, and it's really just a a number. I'm sorry, it's really just an equation. But we could simplify this a little bit more, and we could say set q is going to be r.ks.length. Maybe we'll call it C. C for count, or we can call it L, but it looks like a 1, right? Well, let's call it C for count. And then now we can replace this in all the I only want to replace it in this selection. How do I do that? That should make this a little easier to read, because the lines are really long. Edit selection, edit, replace. Oh, I guess I could have just done it. Find in selection. Okay. So we're going to say r.ks.length, and we're going to replace it with C, but we're going to skip the first two because I made the selection too big. And then we're going to say, how do you do it? Replace. Okay. Okay, so now we can see what the big deal is about. Back to that. I was trying to see if I could hide this stuff temporarily. Like, it'd be nice if I could. Like, I like having that stuff, but it'd be nice to hide that temporarily. I think if I do Zen mode, it's going to go full screen, right? You're seeing a tiny, you're seeing like a quarter of my screen. Oh, we can't even hide that. All right, whatever. Taco bread. Oh, there we go. Taco breadcrumbs. Oh, I thought these are the breadcrumbs. Sticky scroll. Maybe that's sticky scroll. Okay, that's sticky scroll. View. Appearance. And the mini map. That's it. All right, so now we have a little more room to. I like all this stuff, but hard to see, especially when the font is so big. Okay. I was also trying to like pretty print stuff. This doesn't matter. This is garbage. Okay, so all right, so we haven't entered calculation mode yet. So now just so you can see in the code, if you're only looking at the code and just on the screen, I want to keep a reminder of what it is I'm doing, and so that is this. Because this is all I did here was I'm taking the goal that it gave me, and I'm basically documenting it. So I pasted it in here. So we have to prove that this line right up here, which is the expansion of the partition.term, this thing dot term, is the same as just plain r.term, which is this, which is much simpler. And I think the key to this proof, it may be to do this, because you're about to see that like some of what I'm working on right now is very painful. You would think that's a valid operation that you can do in mathematics, but it is not. It is not in Lean, because we are not using numbers as you and I know them and learn them in school. We are using natural numbers, and natural numbers are not well-behaved. They don't have a concept of well-behaved division or subtraction. If you say 5 minus 100, the answer is 0. If you say 5 divided by 100, the answer is 0. Actually, yeah. Eval 5 divided by 100. If we say that they are natural numbers, then you can see the answer right here is 0. If we say 50, then it's going to be also 0. Right, because there's no 1/2, right? If we say 500, we're going to see 5, right? So that's the right. Numbers don't behave the way you'd expect. Okay. So you have integer division, but it's not just integer division, because you don't have division right? Like it's not even the division you get with that I'm used to from you know, programming for many years. Right? It's a different beast, and the rules are not well behaved. Okay, so let's see. So now the very next line is calc, and so that introduces calc mode, and we have to basically, because we're showing this and our goal is an equation, this little underscore at each line is taking this part right here. Basically, we're trying to do this calculation. So we're doing a bunch of you know, starting from this line, we're doing a bunch of transformations so that we end up at this line. And you can see at the bottom, I have this here. And here I have what I think is going to be you know, they're the same, right? So I'm here, I have what I think is the next to last line. This line is garbage, right? It's the same. So if I reach this line, then the proof is complete. But you can see the word sorry is in here. So I need to get rid of this line, right? So this is telling me that, you know, this bottom line right here is a rewrite tactic that can go from here to here. And that works correctly, right? I can eliminate this j because it's j divided by j. And so we get m over c, and then we're good. But you can see I've commented a bunch of stuff out. These are all things that I've tried to do in between. And so the calculation goes from here all the way down here, and when I get this far, and I'm good. All right, so what's happening is the very first step, I'm taking this and I'm saying this line right here is the same as this line right here, and that's what this little equal sign means, and this underscore and equal sign. And the way that we prove that, which I can now almost write on one line, because I did that change to use the letter C everywhere. In fact, I'm going to do this and just, you know, I'm going to make this shorter, right? I'm going to write this a little more compactly. Okay, so let's even move this here. All right, so we got a sum of this thing plus this thing, and we need to get it to this thing. And you see now down here, it's just MC. So at some point, right after we do this, I do a simplification step where I'm going to remove this K and RD. But so in order to make that happen, I have to take the R and D that's here and the R and D that's here and get them outside here. So that's the basic step. So I'll just, you know, again, rewriting from, now that we have this here. Why? Now that we have this here, we'll just take this. I can put it on the line, and we can see them line, you know, step by step what's happening. Which I really enjoy this. Like I enjoy this part, but I don't enjoy the number system I'm using. If I could do this with rational numbers, which I can, had I done different choices in the representation of my my data structure, I could have used rational numbers and everything would have been fine. But I didn't. And so let's see what we're doing here. It would be nice to have a mode in this editor where you could see the, you know, in a calc mode where you could see the differences from line to line as you went along. But I see now, yeah, this is readable, a little more readable. Not terribly readable. It's still a jumbled mess, but you can see like parentheses are moving around and whatnot. So all right, so we start here, and what we originally had, maybe even put this on this line right now. And so you can see the transitions. You know, I know this is not terribly readable when it's all jammed together, but you can see that they stack up, right? And that's the difference. It's easier to see where they change. And so you can see I moved the R and D, the R dot D to the left over here. Whereas it's pretty much solid on this side. And that's the commutative property of multiplication, right? You're allowed to do that. And then we parenthesize this, and I would say add a so. What do I do with that? So the associative property is, oh, I see. So I put parentheses around this whole thing. Right, so so I added the parentheses here, and at the end I added another pair of parentheses at the end. Maybe we can make that line up a little better. And you can see I juggled some parentheses over here. So this is the addition. I wanted to on this line. Yeah, you can see if I put my cursor over that middle thing, it highlights the whole. You can barely see it, but it highlights the whole line. Whereas now, gosh, my cursor over the middle line here, it's only within those parentheses. So that's I parenthesized these. I put the parentheses here basically. That's that's add assoc. Natural numbers add associative. Natural numbers multiply associative is the same thing for over here. I just moved out those parentheses. Okay, and then like this was easy to do. This was not hard. And then, but it's just hard to explain because it is kind of annoying that thing pops up every 10 seconds. Anyway, so then now we have the same R and D on R.D on both sides. So maybe we can illustrate that got moved away. Okay. So now I've got R.D times this and R.D times this, and so I extracted that, and now I have this R.D. Wow. Everywhere you put your mouse, it's there. Over here as well. So this K, this I'm simply removing, right? So that K plus R dot D gets blown away, and then that introduces this little thing that there's a possibility that R dot D is 0, and so you have to prove one of these two things. Which is why I guess I did have this. But it turns out I don't really. I guess that's where I wound up not using that. Whatever. Anyway, so again the OR sign here, the vel sign. The logical operator is called vel for the Latin word for or, and it is the top of the AST here, the syntax tree. So this is the top level operator, which is why it highlights the whole thing when I put my mouse over it. You can see it's an or, and I have to pick one of these two to prove, and that would be a contradiction because RD is greater than 0, so this can't be true. So I pick left, and that's what left does. And so then the left makes that R dot D go away. And then we're back to calculating, and now we've got a simpler calculation. We've got this M divided by C on the right. In fact, now that I've made it simpler, I didn't want to type this before because it was so, because I had all these words spelled out, and it was just so hard to see. So let's put this in here like this. What we'll do show again. Show. And this completely unnecessary. It's just for clarity, right? It's just to make it easier to see what it is we're proving. All right, so we'll put this here. Divided by C plus J times M over J times C equals M dot C. Okay, so bring this over. Bring this over. Yeah, so now we're down to like this part over here. Something like that. All right. So to me, this is all one unit. It's all one little term. We got this modulo in here, so that's kind of unpleasant. Modulo is the remainder operator, so it's kind of weird. You don't usually do that in algebra class, but we do it all the time in programming. And of course here. Okay. In fact, can I do this? No, I can't. All right, so we can just say, yeah, we started either way. This is redundant, but whatever. Well, that's just exactly the same, isn't it? What's missing? No, it's not. Is it? Yeah, it is. Exactly the same. Oh, so I've made no progress here. All right, and okay, and now we get to the pain of natural division, the horrors of natural number division. Because you would think this is easy to replace, right? You have J times M over this. So okay, obviously you can say this, right? Obviously you can say this. This is obvious. But you cannot say this. By what? By what law can you say this? It gives you lots of suggestions, but none of them work. None of them help you get there. These are just suggestions for things you can rewrite. All right, so can you prove it with omega? No. Can you prove it with ring? No. Can you prove it with Linnerith? No. It's because it's not true. that's the problem. It's not true. It's not true for natural numbers because the division is just not the way you think of division. Let's bring this, make it even bigger. All right, so we got to find something in here that is proven, right? That is a theorem we can actually use to. Where's my? I'm looking for the docs. I have so many windows open. Oh, okay. So it's probably this window. This is how to use Calc. I didn't, but this is not the reference I usually look at. Yeah, this is actually lean 3. Begin and end is all lean 3, so it's redundant. Oh. I don't think I've seen this before. All right, you don't have to use equality. You can use less than or whatever, as long as they're compatible. And you can use your own. As long as it's, I guess, transitive. Yeah, transitive. Meaning that if something earlier in the list has the same relationship to the, that it says it does to everything below it or whatever. Anyway, read this at your leisure, I guess. This is what I'm looking for, pages like these. Right, so basically, whenever I've had to do anything with division like this, it just takes me hours and hours to solve something that winds up being one line, but I'm just not good at searching for it. And there's got to be a way to prove this, because I know this works, right? I think there's a way to prove it because I observed that it works. But what do we want to do? What steps can we take from here? I don't know. So we look for things like nat mul div something. Like, all right, what am I looking for? I'm multiplying by something and then dividing by that same thing, right? And I want to cancel it. So I'm looking for mul div cancel, right? Or something along those lines, which is what I'm already looking at, right? Well, this is not exactly it. This is kind of what I'm looking for, right? Let's see, it says m is not 0. Okay, and let's see if this actually matches up. I'm going to copy this and the name of it, right? And let's see if it matches up to what I'm looking at, right? I think it does. It's actually kind of like a whole lot easier to read this now than when I was seeing it before. Okay, so we have, I want to go this way here and cancel out the m, right? This is exactly what we have, right? No, okay, sorry, no. It's not what we have. So let's try and apply this, right? Let's try and apply it here. It's not what we have because of the parentheses, right? You'd think it would be, but it's not. Because this set of parentheses is here. And that's the pain, right? Because now it doesn't work. But let's try it. All right, so we'll say so copy all this plus m over c. And that's what we want to do, right? And it equals a rewrite of this, or by rewrite now mul div mul left, right? And it's going to complain, did not find instance of the pattern in the target expression. Okay, so we can't do that yet, right? We can't do that yet. So can we say this, right? What rule would allow me to say that? Well, omega is going to tell me why I can't do it. Could not prove the goal. A possible counterexample may satisfy the constraints that E minus F is greater than 1, where E is J times M. Right, so this whole expression right here, right? So there's like a modulo thing, right? The idea is that because this is integer division, there could be a remainder, and well, it's just mad about that. And then B is R dot D. B and A are positive. Okay, so J is positive, B is positive. And there's a difference between these two things. So that's why we can't do that step, because in integer division, there could be a difference. You can ignore this arrow, right? It's just saying that J times M, I think the arrow is here because it lifted it up to rational numbers, tried to solve it with rational numbers, I think. And then now it's the arrow is saying convert it back to a nat and to a natural number. And there could be a difference between these two things, so that because as we saw, like 100 divided, or 50 divided by 100 is 0. So that's why that gets weird, right? I wonder if we could do this. What if it allowed me to say C times this well, this is not a can I multiply the whole thing by C over C is what I'm getting at. C times plus J times M divided by JC plus C times this. Oh, sorry, wait, hang on. Divided by C by omega. Can I do that? Am I allowed to do that? No, I got a syntax error somewhere. Gotta say C times this. Is this good? No. Still not good. What's wrong? I gotta put another parentheses here by omega. No, by ESOP. Sometimes omega can't solve it because it's Same thing. All right, so we look for exact, right? Or a rewrite rule that can solve it. No rewrite rules are found. Do we have C is greater than? No. Okay, so let's have this in we can have C is C is 0 is greater than C, and that is R dot H size. That is a property of the rake. Ah, see, now we can solve it. You see it turned blue, and we can solve that by and if that can solve it, then Omega can solve it. Oh no. Maybe ASOP can solve it? Nope. Maybe we can say rewrite of this rule. And let it figure out what the parameters are. If that works. Nope. I saw a sim in there, so maybe we'll try this way. Nope. Okay. So this works. We say r.h size. I think that works. Let's see. Yeah, okay, that worked. So this whole thing has to be filled in, but we can skip over it. Could I have found that with RW? Now that yeah. Well, it's not exactly the same. Actually, cancel left now works. Oh, by rewrite. Div cancel left. What is that? I think that was the thing I was looking for. No, that was mul left, right? So here we want m divided by 0, and m is j here, which is also. Oh, right, but the reason for okay, so the reason we couldn't do that was because of the remainder rate, because of the parentheses. Okay, but we have this, right? So we've made this step. So now we should be able to distribute this, and in fact we can say you can rewrite this thing interactively by going to conversion mode. All right, so this is showing us what we have to work with, and we can kind of explore here. So what do I want to change? Well, I guess I wanted to distribute this C over here. So if I say rewrite, that would be mul dot mul dot no, it'd be nat dot mul add, and that should rewrite it. You can't see it happening. Like sometimes I want to be able to see what the rewrite is, and it doesn't seem to work very well in calc mode. Yeah, okay, there we go. That's what I want. Is it? So right, so It's a distributive. This is a distributed rule for right n times n. Yeah, I want to distribute the n times or whatever. Right. So now we get this. And the reason that I wanted to write the tactic first, because I know what it's called, is then I don't have to, right? But that's not. It should be C here. The C should be here, right? That's what I was getting at. Maybe this didn't do what I thought. I have a syntax error, C times. Ah, okay, so that is not what I wanted. Surely there's a law for that. Come on. Maybe I don't have the parentheses right. Oh. Maybe I'm not right. Hang on. The same thing. Right? Same issue. There could be a slight difference between these two things because of integer division. Okay, so I wonder if I can rewrite the definition to put the parentheses in the place that I want them. Right? But going back to the earlier problem. If I go to term, but no, I cannot. I cannot do this. I need that remainder, that issue with the remainder to be there. So I cannot change this definition. All right, so that was also the way I got around this before. I don't even know what I was going to say. It's like several people have said this, right? That like a proof is finding a proof is like walking through a maze, right? And at every step, you might be in a tunnel that you might be in a part of the maze where the direction you're facing just has no way out. It's a complete dead end, but it looks like there's hundreds of miles of places to explore in front of you. And so you have to be very sure of yourself that, like, do I believe this is something I ought to be able to do? Like, I had hoped to do this step to cancel out this C right here, but I can't do it because, well, I mean, what are the rules for canceling? So, is there anything like mod mul? Like, I don't even know what, I don't have any intuition about what the rule is for that mod mul. Did I use that already? Not here. All right. So let's just put rewrite nat.mod instead of this. Let's get rid of this for a second. Up here. I mean, that did something, but it's not. Let's come back to that. Mod. I have this. Is that what I just saw? M mod K times N over N. M mod J times C over C. That's that. What's this? Where do we do that? It's going behind my little bubble here, so let's shrink down. You can see it. That's not changing anything anymore. But this is changing because I got rid of the model. Okay, so this is promising. Yeah, you got it. All right, so let's copy this over and see what we got. So we sum, hit copy on the sum. Did I copy the wrong version? Yeah, I copied the wrong version. Copy this sum. I wish it would. I have no intuition for how that's parenthesized. So, all right. So it's M over C mod J. And that works. Okay. And we're trying to just get to M over C. So if we want to do this substitution, we have to say M over C divided by J. substitution I keep trying to do, right? Like what I need to do is I need to say that should be a legal move, but it's not. Did I do the parentheses wrong? What did I do wrong? All right, so we have another. So pattern is. Comment this out for a second. Pattern we have is j times, or it's just m over j times c, and I need to simplify that. Or rather, I need to expand it, right? Wait, look at this. X mod A. And so if X is M over C, I don't have M over C over here. I have M over J times. I think there's a way to expand this. That's what I wanted to focus on for a second. But mod plus mul, right? Mod plus mul. This is very close. We're almost here. Let me copy this over. But it has to be A times B. But I'm looking. I wanted to look at the right, this side. See how close this comes. So we have well, okay, this is not what I'm looking for, but so the one I used before was called Nat. That was like a lifesaver for me. Was mod add div. Yes. M mod k times this. Ooh. There's something mod j. Okay, hang on. We can use this directly, I think. But M over K is K. Got a C in the way. Yeah, the C is causing trouble here. I don't think this is going to work. I think we can use this because of the C. Right, it doesn't find the pattern. Okay. So it's something about nat. Maybe like equal div. A over B mod C. A over B mod C. Not the same. A mod. No, not the same. Well, I guess it's just div and mul. So div mod div mul maybe. Like I'm trying to produce a mod of maybe nat mod of. What's the one? So let me look at my little cheat sheet here. First of all, these are the proofs that are working. I had them in a separate file where they actually work. I was going to check this in, but I didn't do it. Div add mod, okay. These are all about less than relationship. Wait, this is what is this? Like it just, I can't keep all the numbers straight. It's like I cannot keep all this in my head as I'm searching for everything. I need better help to search. D times N over D. D times almost the same. Let's try this. Nat div eq sub mod div. What does that give? Okay, but that's not the right place. I don't want to rewrite this one. I want to rewrite it over here. I think. Ooh, and I had a simplification rule that if I could make this happen, then I could do this cancel. Then I okay. So but I couldn't get this. I didn't have this before. But I think I can rewrite this in a way that it is going to make sense. Okay, if I use this rule. Okay, so maybe this is a path to follow. Okay, but I think if you tell it, I want to test whether I can make that happen or make this like find the right place to do what I want to do. So place this with M minus M mod J times C. That works. Maybe. It's taking a long time. Why is it not? Visual Studio is just like, look at that. It's like massive amount of. Sometimes you just restart the server and it does better. I can't get past this. This is causing it trouble. Yeah, okay, so it's that line is causing it. The left hand side. Now of this, we want the right-hand side of the addition. And the right-hand side of this. And then now can we do this? Rewrite. Oh, is it backwards? Oh, no, it's at the bottom here. Oh yeah, okay, it worked. I had my cursor in the wrong place. Okay. We can actually say pattern m over j times c, and then rewrite this. Maybe we can't say that. Yes or no? Can we say it? Yeah, okay, we can say that. Made no progress. Okay. Oh, but did that do anything for me? I applied a rule, but did it do anything for me? All right, so we have j times m minus j times m okay, well, the idea was, okay, so hang on. I think maybe now, because okay, so then the next rule is that d divides this. So j times c evenly divides this. And then we don't have a c. That was why I was talking about multiplying all this by c, right? This is the term I had earlier. Maybe I shouldn't have simplified that. What if I did this step? What if I did this step first? Right? And then, can I simplify this? J, let's see if I can remove these parentheses and still have it work. Yes or no? No, that did not work. Okay, hang on. Okay, but now I think I can remove this. Yes, I think I can remove this now. But how do I do it? I think if I do this, sorry. Okay, just to make sure it's syntax or the parentheses were balanced. Okay. I won't be able to say exact yet. I have to prove something first. I have to prove this thing. Yes. Okay, so I have to say to make this work, I have to have this lemma or this fact. So not D, but wait, am I on the wrong line? Yeah, I copied something wrong. Hang on. Yeah, I copied something wrong. Start back up here. I don't even know what I did. So let's comment out this line. This is all garbage. This is what I'm trying to write. Right? I don't even know. This is okay. So this is the line where I moved it earlier, so I can delete that now because I moved it up here. And now that I have this, I believe, let's copy this again. I believe I can remove the J and this J. By exact something. By exact what? I can't find it. I didn't expect it to find it. I need this fact. Okay, so now I have this fact. So first we're going to have this, but it's not D. So this is M, and this is M. Maybe I can't remove that. because the C is interfering with things. Like it's almost this. Almost this, but it's not quite this. Let's see if this is true. So is J, does J, this little symbol means divides. Does J divide J mod J times C? I don't think so. I don't think that's true. Not true. That is true. I need to get a C in there somehow. Okay. Can I say that? My friends are not balanced. No. It worked. Okay. But can I say this now? Probably not. It's too good to be true. Oh. But can I say J times C? Okay, so then that's at molcom. Molcom. That's so weird. So C times J works fine, but by and that was rewrite what? Something exact. It was exact or whatever. No. Okay, so exact this. This should be obvious, right? Should be a very simple rewrite. Yeah. Okay. Now, no. All right, well, this law now works. I can apply this law now if I have it in scope. For all ND nat, and then by sim. Now we get this by sim. It didn't work. Something's wrong. Nat div mod d times n over d. Wait, am I going backwards? D, so this is D times n minus n times divided by D, which is D again, over D. The parentheses are off. Now, okay, so now I have to have I think I couldn't do this step if I didn't have the wow, this is just so ridiculous, right? It's so tedious. It's kind of fun, but it's like it's tedious. I want to remove one of these parentheses and move it right here. And that should be I'm not sure. First of all, let's see if I can even get there. Right? Like if I have this one. Yeah, I can. If I have this, I can get there. So how do I? Because ESOP works. Right? And then if I do that, right, then it should be the case that we have all of this over C. No? So we still have some mod stuff to take care of, but I think it's all going to cancel out. And this is like a horrendous proof. Like there was, okay. One thing at a time. See, because we have the same thing. So we have this over C plus this over C. Ought to be the whole thing over C, but we have to do with the mod stuff. So it would be like div add div or something like that. Add div. No, I don't know. But like these two terms would now almost be exactly the same, except for this extra m minus. And then I was able to get rid of this, right? So I was able to turn this into m. Oh, but I lost what I did to it. Ah. Oh, this right here, right? No. All right, well, I'll have to find it again. But I was able to remove that at some point. All right, but the question is, can I really do this? And I think I can. And the question is, I think this is the magic thing that puts it back. We'll see. Magic incantation. All right, so I had this a second ago, but I lost it. So let's change this to J times C. J times C. Oh, but it's M. The statement is true, it's just I don't know what N is. Okay. Now, but I actually I'm trying to get to this. I'm trying to get it just to this. I'm trying to cancel these two out. That's what I want. It's looking for something, but it can't find it. Right, so we had this line, so J times, let's just call this D. Set D is equal to J times C, just inside this proof. Set N is equal to M. And simp can find it with this. Yeah, but it doesn't like, I think I can't use this syntax here. But at least we know it works, right? So every time I see a D, I will replace it with this. I probably could do search and replace inside the. Wait, isn't this nat div mod? Which I have up here? Yes, I do. Okay. Come on. It tells me it looks like it's working, and then it doesn't. N and D. Okay, so we got to say J times C M. But it's not. Does it tell me it's not right? So of the big thing we're doing, we're on the left hand side of this. Then we go to the right hand side of this plus, right hand side. Does it apply? No. Left hand side. Do I not have the same pattern? I can't do a search in here. I'm looking right here. We have J times C is one term, right? That's D. And the arguments of this thing are N and then D. So I have the arguments correct the first time. What if I just said sim? Rewrite at div mod. No, it doesn't. Is this? Oh, I still haven't done this step. So I've got a step in here that I'm missing. I haven't removed these parentheses yet. So if I have those parentheses, this yellow parenthesis ends there. Okay, so I need to have. It's not at all clear to me how these are parenthesized, so. Oh, now the structure is different. So I have to navigate the structure differently. Wow, this is ugly. It's just ridiculously ugly. No, I'm in the same place. A times C. How is that not the same? Wait. All right, so it's parentheses again. What I need is to be, I need the whole thing over this. So that's actually correct. This is the right step. So inside these yellow parentheses, I think it's the same thing. I have, all right, so yellow parentheses right here, d times something. No. Purple parentheses are here. Inside, here they're purple, here they're yellow. And then I have, inside of that, I have a second pair of parentheses. Divide, that's the same. Well, obviously this is the same. Right, because that's just removing some parentheses. This is trivial. This is not important. Not even the next step. But this should work. That's weird. Look at that. It's not doing what I'm asking it to do. So this is saying, right, like this right here and this right, it's this. This is the same. The only difference is I put N and D. So I defined these things. So I'm confusing myself every time. I should probably change them to D and N, right? right? Because D is on the outside, so that's the first thing. So that now I'll switch this around. Okay, well, I don't even pass in parameters here. But D is the J times C, right? And if I rewrite this, then this pattern, D times oh, it's not the same pattern. I have this pattern right here. So this is what I want, not nat div mod. I want nat mul div cancel apostrophe. But I have to prove that this is. See, it introduced a goal that I have to prove that this is divisible. You know, I did this a minute ago, and I added this line, right? And that's not what I wanted. I needed this line because this is the proof I want. I just need this. This is the line I want to execute. So okay, I confused myself. Okay, so we can actually write it like this now. All that nonsense was to obtain this expression, right? This should be M. And then I think I don't even need the conv to get down there. You see, like, I think the computer should have found that for me. But it does not. And that's the problem. Like, the searches don't find the thing for you. So one of these days, well, probably what will happen is that one of these days I will switch over to using rational numbers, and then all these problems will go away. Like, I've been scared to do this because I'm so far into the development cycle. I'm scared to like change the nat numbers to rational numbers because I'm afraid it's going to break everything. But if that doesn't happen, then it would be cool to just, you know, learn enough about Lean to like write a solver for division in natural numbers. Okay, so now we're moving along, right? We've made massive progress here. Well, some progress. Okay, so this is redundant. These things are redundant. In fact, I think this gets me. I don't even need it. This is just, there's no search involved in that. All right, so that line is done. So what do we want this line to be? I'm still working towards way down here. Oh, okay. I think I can cancel these things. All right, so I think the left-hand side I canceled this way. Like this. I might have, this might be the wrong rule. Let's say m minus m over c. Is that the right rule or not? There's such a lag here. Yeah, okay, that was the right rule. And I cancel the right-hand side, so I don't need this. I think I can get m over c by something. I think that's legal now. No? But it's not. Net divide sub mod. No, I'm mixing up. That's the wrong thing. That's this. That's this symbol divides, not division. $5 in the morning again. Because that's exactly the same. All right, we're never going to get here. And I also don't need this because I never used it exactly. We're almost there though. This is the last line. This is all I need. But I thought I would be coming from this line, but I'm not. And that's the same. Like this line worked, but submod div or something like that. Div submod. Div equals submod div. I think maybe this is. All right, so let's look at this. Rule is this: div equals submod div. Do I have this? I think I do. Am I looking at the right place? All right, we got C over here. We've got M minus M. We're almost there, except for the C. Except for this. not quite there. We're going to try nat, or let's just try rewrite nat sub mod div equals sub mod div. Ooh, that worked. Did it rewrite the right thing? No. So we want to go conv. We want to go left hand side, right hand side. And we want to rewrite in the other direction. And I don't think we can because it doesn't quite match. Because of the J. It's more like mod mul or something. I don't even know if there's such a rule. Mod mul. Div. This is promising. So this says m mod. Let me see how this. This is what I want, but I can't do it because the subtraction's in the way. Right, the m minus m here. If I have to break apart the subtraction first. Yeah, so let's write down what this rule is. This is like I'm trying to formulate a plan here. This, and we want to go which way? We want to go. So then first break up the subtraction. So we have like sub div something. Sub div sub div same. But that's it. You need a division ring to do that. So I need the nat version. B is positive and B is less than A. And we can do this. We have to have this plus one term, but so A minus B over B plus one A minus B over B plus 1. That's not B plus 1, is it? Or if I could merge these two terms together somehow, right? Like div add div or something. So div add div or divs div. Let's do nat div add div. Or just div add. That's not what I'm talking about. Or what about div cancel? Maybe I can just bring a C in there somehow. M times N over N is, okay, that's right. M times N is M. So close. But this, okay, so there's some rule about this here, right? This is nat mod submod. A divided by, or A mod B is A minus B mod B. A minus B mod B. That's not. That's not what I have here. Right, because you can add and subtract B as many times as you want over the modular rate. I've seen this. I already looked at this one, didn't I? This is saying if you multiply by n, you can divide that out. N minus. I have mod instead of multiply. Just like cancellation rules. Cancel. That looks like it ought to be so easy to cancel. Something. What is this rule? Remind me what this is. Print. Or check, I guess. It always annoys me you can't do that in the middle of. This is all wishful thinking. I can't look this up because my computer's too slow. Put it in over here and we'll find it. Yeah, this is not going to happen here because it's not. my brain can just not process this. I need some kind of like cognitive support. Okay, so M minus M. So that's another promising theorem. So I've got two promising theorems here, but the thing I've got is just not quite the same. Ideas. I break up the subtraction. Can I cancel out that J somehow? I don't think so. It'd be like mod mul div. Mod mul div. Oh. Mod mul. I'm looking to see if. Wait, is that what I'm just looking at? No. Mod mul left itself. Right, that's this. That simplifies this, but I have the subtraction first. Okay. I need both of these things, but there's some combination of them that I just don't have. The question is, can I get rid of the C though? That's so it's like this is not the same thing. M. Well, let's see what that proof is. Let's see what this proof is. Mod of divide. Mod of divide. Okay, so mod of divide. What is this? Could very well be that there's just like obvious arithmetic laws that I'm not familiar with. I just don't do this kind of stuff often. They're not obvious to me. Like, I feel like you could just remove that J, but you can't really. But like, because it's over the. No, I mean, like I don't think you can't really do that. Okay, so you put the J back. The intent is that, like, if this were just math class, I'm pretty sure, and I had rational numbers, I'm pretty sure that I could say this, and then I could distribute this division. You know, either I could just do this, right? Right? Like I could distribute that. But you can't. Because we're dealing with natural numbers. And division doesn't work the way it ought to, the way I expect it to. Right? Bad because of nat division. Because if you could do that, well, then you could just right? You could just remove this. Right? This would all cancel out, and it would just be m over c, and then it would be done. And that's the proof. That's it. By what? By exact. Come on. Come on, you can figure this out yourself. Oh, so wait, hang on. Did I rewrite that in place? Is that my problem? Oh. Well, this doesn't work either because because you got a subtraction in there, and subtraction might not by omega. Yeah, you can't do that. But wait a minute, can you do this? Well, put the parentheses back. Yeah, you can obviously do this. You can obviously swap these around, right? Sorry. Why can you not find that? This is by rewrite nat mul addition is commutative. Right, that is legal. And then once you have that, now it's also associative. So we say we can remove this. So, oh, okay. So that law is not allowed because this is a subtraction over here. All right. So, but I bet that is a law. Yeah. Okay. So there you go. I don't even know. Like this is so. If these were integers, this would be obvious. If these were rational numbers, this would be obvious. But they're natural numbers, and you just can't do this stuff. Okay, I need to get the plus and the minus next to each other. I don't think I can do that. Like you would think this would just be m, right? This one right here, m minus something plus that something. See, the problem is it's not true, right? Because in, right? Check. So let's say m is 5 minus 100, right? But when you evaluate that, you get 0. So 5 minus 100 plus 100 is 100. When you would expect it to be 5. So subtraction is screwy and division is screwy. So, but there's got to be a trick to this. But maybe this is just not possible. I don't know. Maybe it's just not possible to prove this with natural numbers. And maybe what I should do instead is just see. The problem is that this is all about primes, and primes are defined for natural numbers. Is there such a thing as a rat prime? A rational number that's prime? I mean, maybe I could somehow have partition take rational numbers and then that's the problem. I don't know how to fix this. I don't know how to get out of using natural numbers. Like I think if I do that, I'm going to wind up rewriting like almost, or at least have to touch almost every single line of code. And so that's my problem. Wait, but if I do this ought to be able to cancel, right? Like if it's just in this order, right, you can't remove the parentheses because this happens first. What is C? C is the length of the list. So M could be much bigger than that. So that doesn't help us. I'm just stuck. Can't break up this subtraction. Well, hang on. This. Surely this is less than or equal to this. So we could say have M is less than M mod J times C, right? Or other way around. M is greater than, it should be less than or equal to M equals by ASOP, right? Why? Because this is 0? No. M mod. We have J is not 0. But J is positive, and we have C is positive. Okay, you know that. You don't know this, huh? Oh, okay, you do it. You do know that. I wish I had a tactic that would just like try everything and like search for things. Like Isabel has a tactic called sledgehammer that just like just tries stuff and it just keeps trying stuff. Aesop is a little bit like that, but it doesn't. Okay, so now if I have this information, I still need to prove this. Can I prove this now? I can. I prove it without this fact. Oops, this fact. No, I need that fact. But I can prove without this fact. Because that's, I mean, that's basically skipped over, right? Because this like requires no proof. And so what did I do here? This was the getting rid of the C. And this I do know how to get rid of, right? Because this can be, we said that this is M. Wait, this line is the same, right? There's no difference between these two lines. This is exactly the same, right? I don't see a difference. But it hasn't turned blue yet. But yeah, that's exactly the same. Okay, so it's only this one line that's causing me trouble. And the trick is, what I'm trying to do is just get rid of, yeah, so this is a division problem, right? I'm trying to move this parentheses around here so that, right, that this thing over C I got two things over C now, and I want to factor that out, and I can't do that. So what do I do? What does this mean? M minus M mod something. Can I put, can I do this? Like undo this, undo what I did here. Except now, like, okay, this was I had j times c there, but what if I put that j back without the c? Right? So I do this. I think I can do that. I ASOP. No. I exact. Right, so it's something like it would be like mul div cancel, but like but in reverse. But I need nat. Nat mul cancel. Mul div cancel, okay. There's also div mul cancel if this isn't right. Nat div mul cancel. Wait. Oh, mul div is over. We don't have. Okay, that's right. Oh, it's this rule right here, right? Like this is what I want in reverse, I think. Oh, but I need like a div rule. Nat div. Not really. That's not quite what I'm looking for. The idea would be that I take this whole structure and I add j and like basically take this. Oh, sorry, I had it wrong. So why is it? Okay, so this exact thing, and then I'm just going to put parentheses around this whole thing divided by j. Why? Okay, what? Something's wrong. Yeah, divided by j, and that is by this rule right here. Not mul div cancel this, same thing. But I need n divides m, which is not true. I don't think. N evenly divides m. rewrite. And I don't have a proof of that. But I have this rule down here that I can force something to be. So have D divides. That would just put this back though. I don't want that. Right, so when you normally the reason that it doesn't work is because you have to have this add mod div add mod and div add mod because you need this. You can always take something that's an m and you can always replace it with n over m plus that thing. So instead of just doing this, you could do one of these two things, mod. Okay, so m is also one of these. M mod k plus k times m over k. M plus wait, is this? Is this? No, this is almost the same as this, except the problem is that the subtraction is in the way. So you can't quite do it. It's so annoying. Like rational numbers work. So it would work so easily. There's a tactic called Qify, right? But I think it's working in the opposite direction from what I want. Does it come up in here? I don't think so. You have to say, where would you go? Outside of this, we would say, sorry, help tactic Qify. Huh. Okay. Yeah. Maybe I don't have. Maybe I have to import Qify. But now I imported mathlib, and so it's going to take forever. So while that's running, I will keep looking for stuff. I'm pretty sure Qify goes in the wrong direction. But it moves you into, it takes theorems that are defined for the natural numbers and moves them up into the rationals. And maybe there's a way to do that. Maybe there's a way to just like lift everything I'm doing up into the rational numbers, prove it for the rationals, and then like work back down to the natural numbers. I don't know how to do that. And so I'm just like every time something like this, subdiv, what is this? Same x minus 1 stuff. So this is, I still want to come back to this idea. I removed j over c. Can I add this here? No. All right, so we have to put this back. That was a mistake. I didn't intend to delete that. Sub div. Only for nats. Div cancel. I think I'm just going in circles at this point. All div cancel. I've looked at these. Div cancel, right? What is it? Cast. Vision semi-ring. I don't have that. Cast div. QFI come back. What's the problem? It wouldn't let me import math. Okay, so I've already got this somewhere. It didn't like that. It didn't let me import that. Because I'm probably already importing it here somewhere. It's so slow, you can't even navigate when you're in Lean. Like normally Visual Studio is like super fast, and like only 900 megabytes right now. So earlier it was like 2 gigabytes. It's just ridiculous. It shouldn't be that. Yeah, I don't know. Like if I could just break the subtraction up, like why can't I do that? What is preventing me from doing that? put this back how it was. Move plus. That's exactly the same. That should not make a difference. Oh wait, I'm missing a. That's just adding an extra parentheses there. Parentheses, okay. Yeah, that's exactly the same. I just moved the plus sign. It's so slow. Like, why is it? This is exactly the same, and yet I've unexpected. Yeah, that's from like minutes ago, seconds ago. Now we're up to over a gigabyte of RAM. And it's not dropping. Maybe if I restart this thing. And let it run while it. I don't. Div add mod. Like you can always take a number and rewrite it backwards to get this. And give it an M and a K, any number. Any number you can do that for. And so the thought was inside of here, what I implement, I introduce J. Over J. Okay, which one am I doing? I'm doing this one right here. So you take the M and you do the div, the mod and the div. Okay, so this would be M mod J plus, wait, not M mod J. It would be all the, it would be this whole thing, right? Plus J times this over J by mod nat, by nat mod add div. By rewrite nat mod add div. I screwed it up somehow. Backwards. I don't know what that means. Pattern is a meta variable. Maybe I have to dig in. Like sometimes it's just so easy to do these proofs, and sometimes, I mean, it's not very easy to do the proofs, but sometimes it's like, you know, reasonably achievable. And sometimes I get into this, and then if I show it to somebody else, they'll solve in like 2 minutes. But all right, so again, we're debugging the entire expression that we have to do, which is the this is equal to the goal, whatever it is. So that we're on the left-hand side of this, and then we're going to go, so we're digging into it. Oh, I guess we can start here. So we're on the left-hand side of this expression, and this is a plus, so we're going to go on the right-hand side of that. That's this plus sign right here. And then now we have this, and then we're going to go to the left-hand side of that. We have m minus, right, and that's the whole thing I want to do. And I want to rewrite this. Pattern is a meta variable. M, I have to fill in what? J? No, I have to fill in J and this thing. Okay. Oh. Oh, because it doesn't know what I want to replace, because I could replace anything in there. I have to tell it to replace explicitly this. Or to wrap this. Right, so okay. Because otherwise it could just take its pick of anything that it wants to. Did I do it the wrong way? M minus N. So M is the thing I want to translate, and J is the thing I want to wrap it with. J, so M mod J, J times C. No? Yeah, mod J plus this over J. Okay. So then I wrote it wrong over here now, because why is it mad? We have M in parentheses, M minus M mod in parentheses J times C mod J plus J. I don't even know why I'm doing this. It's just divided by J. Yeah, that's it. Why is it mad? M mod K plus K times N, M mod J, right? In purple parens, that's right, plus J times, in parentheses, Oh, I see. So this goes inside the parentheses. Well, what did that do for me? Well, I guess the question would be, now can we do simp? Simp does nothing. We can't break that up in any way. Like this was a pointless thing. I'm just wasting time. I'm making it more complicated than less. Like I applied a rule because it matched. Like I'm just being stupid now. I think I think maybe the thing to do is just stop. Maybe I will stop and oh wait. No. I'm just gonna reintroduce the thing that I want to be there, which is just this. If I could do that step, then the proof works. Right? That's it. That's the only step I need to be able to do. And it, like, you would think that, why is it not true? Right? So you want it to be true because you think like 5 over 100, which is 0, plus 5 over 100 is going to be 10 over 100, or we'll say 7 over 100. 7 over 100 is going to be 12 over 100, which is true. If you say 99 over 100 plus 7 over 100, it should be 108 over 100. And that, I think, is not true. False. Not 108, 106. Also false. I think if you put all this here and you say rat, you can't do it that way. I don't know how do you force the entire expression to be a rational number. Maybe you do that. Now it's true. If I could just make these rational numbers, then everything would be fine. If I could do this one step, everything would be fine. I think what I'm going to do is stop working on this right now. I'm going to just write up a very simple version of this and post it to the Zulip chat and see if anyone can prove it. I mean, I could ask ChatGPT. ChatGPT never has an answer. That's fine. Claude sometimes is able to do proofs. But it's not true, so that's the problem. It's not true for natural numbers. You would think it is, but it's. I mean, I would know it's not. But see, the problem is to cancel this C. I can cancel it on the left-hand side, and I can. And I get this, M over C mod J. And it works because I don't have this subtraction. And if I didn't have the J, it would work. And if I had a J down here, it would work. That's how I was able to cancel. Like, is this just, maybe this whole thing was just a massive wrong turn? If I backtracked all the way up here, could I do it? That's the problem. It's like I said, it's a maze, right? So okay, that was the wrong. Not this, but this. That works. Okay. You would think he'd be able to cancel the. Wait. Can I do this? That's nat div cancel. One of these left. Nope. Nat div cancel. Div mul cancel. So I just looked at it. This is it. M times n over m times k. There's something that's not letting me do it, right? K times m over the m is on the, or the j is on the left. And I can't do this because of the parentheses, right? Right, it's going to say it doesn't match this pattern. Oh, M has to be, or J, or we have J. Okay, so here M is the M times this. We have J times this, and J is less than 0, greater than 0, is HJ. We need the K as well, and the K is C. The K is C. No. This is an M. J times M over J. Right, it can't find this because the J times M has to be in parentheses. But I just saw, okay, M times N is parenthesized the wrong way. You can only do this step backwards if C divides M is just an arbitrary constant, so you can't do this step backwards. And what do you do instead? Well, you so I introduced this mess, right? Like I introduced this mess up here, trying to eliminate this thing. And so this is a wrong term. This I trying to eliminate I just don't even know. Yeah, you know what? I'm gonna stop. This is going nowhere, and I'm just wasting time at this point. I mean, it's fun to do. Some of this stuff was fun, but like I think I think introducing this term made it unprovable. And why did I introduce it? Well, because I thought I'd be able to cancel this out and cancel out the... See, if there were a plus version of this, you know, which there probably is, div equals... Why would I introduce subtraction? But because this was the one I had. But I also introduced this C. Like I need to write like why I did it. Like what am I trying to accomplish? Because otherwise, if I don't do that, then what happens is I lose track of why I'm doing something, and I'm responding to the thing in front of me, and it just like a maze, right? You're in a maze, and you gotta keep track of where you're going and why you're going there, or you get confused. Or at least I do. I need to write down like what is the strategy. So I am gonna stop like very soon, but so if I could prove this line, I would be set. Yeah, I just, like I said, like many hours ago, I had a different a plan of attack on this proof, right? I thought I was going to be able to make use of this statement, which is this, or I guess this theorem right here. And maybe if I went down that path, because the idea would basically be, you know, to establish that, you know, first invoke term if and only if, which is something I wrote. Write this down. Not in sorted. Not in sequences. Not in sorted. Dedupe. It's in terms here. It's this thing which I wrote in my last video, right? It says what a term is, and then if you can take the term exists, and if you can establish this fact, then you can rewrite that as that there's some constant for which this applies, right? And then the thought was, okay, now for every constant that I have in the new system, like, you know, after I do the partitioning step, well, I have a formula that relates it back to the old way of thinking, right? The old not the old way of thinking, but the old constant. Every new constant is related to the old constant by this formula, not by this formula, by this formula right here. This formula, which is ugly because it has this proof in the middle. But basically, the idea is that for every, you know, here's the constant, and this constant I, whatever I is, I can relate it back to this thing. So like, maybe what I should have done, like, to make that proof possible, and the reason that I went wrong in the first place, I should have said this. Instead of this, I should have said, or I could have said, for all m and n, that if that term is equal to m, left and right, then our term is equal to n. And if I had proved that statement, then I could rewrite each of these, each side of this thing would match with the idea that would match my if and only if rule. Match this with term if, right? Which is this rule right here. And then I could just make an argument based on the, then, or I don't know if I should have said, but I had say this to approach it like this. Then translate each side into, you know, the K form and show that both have constants, so that I can express either side in terms of the other, given partition KS, which is this line right here, given the formula, right? It relates this I to this I, and also the different RDs. Right? So it relates this to this. or I guess the missing factor is the J. The J is the number of terms you're splitting it into. So here, here we're splitting it into 5. So we're starting with 5, 7, and we make 5 copies of, we do this transformation here. We fill in 0 plus 5 and 1 plus 5 and 2 plus 5 and 3 plus 5 and 4 plus 5 for both of these statements. Right, so you wind up with 10. So you multiply the length of the list from 2 to 10 because you stuck a 5 in there. If you put a 7 in there, you get 14 and so on, right? Whatever the length of this times this number gives you the length of the new list, and then calculation gives you that. So anyway, and then the J is also used to multiply to get here, to get the new delta, and the new delta. So R prime D is equal to RD times J. And then you should be able to argue either way that the two things are equal. You should given that information. Then use term if in reverse. I don't even think you have to do that. You don't even have to do that. So the proof basically should execute in parallel. The same way that I did for sort here. Sort proof is the same thing because, well, almost the same thing. Here we say that there are two, there's an M and an M prime. The M is different. You plug in a different M and you get the same number. And here you plug in the same number, you get the same number output, but for a different, but the formula internally is changed. And we just have to show that the formula is the same, or the formula is equivalent. Well, my plan for doing that got short-circuited because as soon as I did this and I said, well, simplify all this stuff, I just got a formula here. It gave me a formula. Lean figured out this formula, but I don't know how to simplify this formula. And so what I should have done, rather than saying simp partition here, right? I start with this thing. I say simp partition, and you get this mess. What I should have done instead, I think, so I'm going to give this, for the next time, I guess. I'm going to say, right, is that I should have made this statement. Because I wasn't able to transform this statement into the form that I could use this rule with. Put this under here. Or maybe. And so and because I stated it that way, what I should have said is this. Okay. Equals n. And then say so. Intro m and n. And now I can say rewrite term if. Now you have to say, I say apply if and only if. I have to break this up first. If and only if intro, and then all goals, rewrite term if. And that gives me two goals. No, what do I do in sort? How was I able to do that in sort? Oh, I have to introduce something and then introduce a hypothesis and like that, right? So on both sides, so I have to, I have to prove both of these arrows, both directions. So it has here the partition is equal to the partition stuff implies the term stuff. Here the term stuff implies the partition stuff. So on all goals, I do both of these things. I take whichever one it gives me and I introduce a hypothesis and I rewrite that hypothesis in terms of with term if. Exist M. I need to like revert the n. No. Not for all n. Well, okay, so for all n, something like that. And then here, is there a push qualifier? No, I have push neg, push exists. I don't know. That's my alarm telling me to wake up. I think we say we have to say term if m, right? Apply if intro n and m. I'm not really. I haven't really done it this way, right? I guess we would just say have term if. You have to like bring it into scope somehow. So we have to say R term if for all m. And now we have the rule customized for. So can we say apply this? No. Because it fails to, it doesn't, it says fails to unify this with this. I need to put like a something. I need to do something with this. I don't know. I don't know. Like I'm not thinking straight right now. Been up way too late. So it's R term m. And you can say I don't know. I might need a special version of this rule because it's not quite the same. Because before with sort, the way I used it before, I have two different m's here, and I want to show that they're the same. Like, does it matter that they're the same? Maybe it doesn't matter. Because I can just say use the other one. I don't think it matters that they're the same in here. For all n, exists m is equivalent to exists m such that our term m equals n. Comma. Yeah, I don't think it matters. I think maybe even here we say right. Now, in this case, I have another m. I have to show that exists, that this m exists. And down here, I have a hypothesis. And I need to specialize this hypothesis. So now we have to break it up a little bit. But in the first one, we would say use m. Right? But we haven't proven the facts yet. So do some stuff, and then use m. See if we could use sorry here, because the facts are not true. But in fact, the same input, whatever, sorry, and eventually use m. Eventually use m. And then for the second case, it's also sorry, but eventually specialize the hypothesis using m. There we go. So that's, I guess, kind of the outline of how I thought I was going to do it. And I didn't do it because I used this symbol, this equal sign, instead of this. And so then it derived a formula for me. And maybe I could have figured it out. Maybe there's a way to make this happen. But I think just putting that character right there was just a wrong term to begin with. I should have written it like this. And then I was on the path I would have planned to do. Anyway, okay? And I wouldn't have wasted 5 hours. You're in the maze, and you get better at being in the maze, right? So you learn the tactics of being in the maze, but you're lost, right? So it's like being in the woods and getting lost in the woods is a reasonable way to get better at being in the woods, right? Provided, you know, you're not eaten by a bear or poisoned or, you know, whatever, starved to death. But getting lost and trying to find your way back is a reasonable way to build your skills. And so I don't feel like this time was entirely wasted. I feel like it was wasted in terms of in the sense that I could have been spending it on this approach and not on this approach, and then I would have gotten further towards my goal of proving this prime sieve works. But at least as the compensation prize, I got more experience and learned some. I don't know what specifically I learned, but I got more experience with working with these, you know, the calculation-based proofs. So, hooray! Anyway, yeah, that's what do I call this thing? Something about calc mode. There we go. And the horrors of natural number division. Well, there you go. So, thanks for watching, and hopefully you got something out of this. And I'll see you again soon.